slides of surface area. And this next example is a rotation about the y-axis. And the way I think is the best way to approach these surface areas where we're dealing with the rotation is right over here. I think it's easiest if you're rotating around the x-axis to use a dx. So if you're rotating around x, you're thinking of dx. And if you're rotating around the y-axis, think of dy. It's probably you can mix and match, but then it kind of creates more of a shell method, which is fine, but it's a little more complicated. It would work. But that would be my advice, is get that down first. If you rotate around x, use dx. If you rotate around y, do dy. If you can get that down, fine. Then if you wanted to, you could sort of think about doing it. Okay, I'm going to rotate around y, but I'm going to use a dx, or I'm going to rotate around x and use a dy. Again, that would be more like a shell method approach, and usually the shell method is the most complicated because you have two directions going at once. So to keep things as simple as possible, if you're going to rotate around y, use a dy. That becomes a little more complicated if they give you your function like this. So they've given us a function of x, but they say go around the y-axis. So what we would need to do here if we want to follow this guideline is that we would need to solve this for x. So we would end up with x squared equals 4y, and then we would isolate the x. And because we are in quadrant 1, where x's are positive, we would choose the positive square root here. So we would end up with 2 square root of y. So this is our function presented as an x value. The original presentation is as a y value. So originally it's measuring height, now it's measuring width. So if you're going around the y-axis, this tends to be a slightly better way. At least it's a consistent way to get at this. So the other thing we would have to be aware of is that these are given to us as x limits. So the x limits are down here, 2 to 4. And we would have to convert those over to y limits if we were going to think about using a dy. If we're going to use a dy, we would want to be looking over here for our limits. And so those limits are going to go from 1 to 4 on the y-axis. So our setup will then be that when we do area of a surface of revolution, we're picking a point element. So I'm imagining this point rotating around the y-axis, creating a circumference, which is what the 2 pi r is. So that's the circumference, 2 pi r. And then we multiply that by ds. And ds converts to, in this case, a dy expression. If we use a horizontal element, we want a dy. So we need to convert this ds over to a dy expression. All right, we'll need the derivative of our function. So we have that our function is 2 times y to the 1/2 power. The derivative of this function will be y to the negative 1/2 power. Bring down the exponent, subtract 1. And we might as well just square it right here where it's a little simpler. If we square it, that'll give us 1 divided by y. So our surface area is the integral. The y limits over here are going to be 1 to 4. And then the 2 pi times the radius. The radius is this horizontal distance. That's an x value. It's measuring horizontal distance. That's our function. 2 times the square root of y. So that's the radius. That's the distance our point element is from the axis of rotation. And then we have the ds part. The ds part becomes the root of 1 plus the derivative squared. And then we have the dy. So that is our setup. Is there any question on that setup that you have? Circumference, 2 pi r, times ds. ds is arc length. And then we're back to the pair of roots. If we have a product of square roots, we can turn it into one big square root by multiplying the insides of each. So in other words, we take the y that's inside this root and we distribute it to each of the terms inside the other root. So this will become a y plus 1 inside the square root. And then we can integrate y plus 1 to the 1/2. We do the power rule, so we're going to take our y plus 1. We're going to add 1 to that exponent, make it a 3/2, and then we're going to divide by 3/2. And there's no reverse chain rule business going on because the derivative of this inside is just 1. If that was a 3y plus 1, we would have to divide by 3 to pick up that reverse chain rule. So our final answer here will give us 8 pi divided by 3. Plug in the 4 here, we get 5 to the 3/2, which we normally would write as 5 root 5. Minus, plug in 1, we get 2 to the 3/2, which we would normally write as 2 root 2. And that will be our final answer. Anything there you want to ask about? So again, the main rule of thumb that I recommend is that if you're told to do a surface area around the y-axis, use a dy, so solve your function for x. If you're going around the x-axis, solve your function for y. Generally is going to be the most straightforward way to think about it. So let's try another one. So this one, also around the y-axis. So going around the y-axis, write your function as an x value. Oh, they already did that for us. So this is set up already in the easiest possible way that if we're rotating around the y-axis, we're thinking about this as our point element that's going to rotate around, and there's the distance it is from the axis that we're rotating around. That r is horizontal, so we want to write it as x equals something to measure horizontally. So this one is already set up in the most natural way possible for a y rotation. We know that we are going to need our derivative of the function, bless you. So we're going to take the derivative of this, we bring down the power, subtract 1 from the power, and then we multiply by the derivative of, oops, that's a 12, not a 2. Then we multiply by the derivative of the inside here, so that will be 12 minus 2y. And then we need to square that. Maybe it's easier to do that before we stick it inside the big square root, so let's just square it here. So let's see, this is a square root in the denominator, -1/2. So squaring that will just turn into whatever this base is in the denominator. So we'll end up with a 12y minus y squared in the denominator. This 2 is in the denominator, and if we square that, it becomes a 4. And then that's in the numerator, and if we square it, we can FOIL it out, or we could just wait. Let's just wait for the time being. We'll see if we need to FOIL it out. All right, so there's our derivative. So surface area will be the integral then. They've given us y limits, so that's all good. That's matching. We're thinking about our interval is right over here. We're integrating along this interval right there. And 2 pi r. Again, that r is measuring horizontal. Horizontal means function of y, which means write it as an x value. So this, you call that a function of y, or you can say you've isolated x, or you've written it as an x value, however you want to think about it. That is going to be the radius right there. So square root of 12y minus y squared. The Zamboni. So glad we're not on the edge. So now we have to do the ds. We know that that's that big square root of 1 plus the derivative squared. We did square our derivative already. It's right here. And we are going to have to distribute this inside across here and then simplify what's in here. So we will need to FOIL this out. So let's do it now. So that's going to be a 4y squared, writing it in descending order. Let's see, 12 times 2 is minus 24, and then we double it, so we get minus 48 times y. Then we square the 12, and we get 144. All right, and then then the division. So that's that. So x prime squared, so we've got the denominator now, so that's 4 times 12y minus y squared, all multiplied by dy. And then we have to simplify before we do our integration. Once again, a product of roots is a root of the product of the insides. So this inside right here gets shared. It gets distributed to the 1 and to this fraction. When it gets multiplied by the 1, that's easy enough. We're going to get 12y minus y squared times 1. And then it gets multiplied by this fraction, and we see that it cancels with this factor in the denominator. So the denominator simplifies to just a 4. Well, that 4 can then be distributed into the numerator. So this 4 we can cancel with the 3 terms in the numerator. So what's left after this cancellation there is going to be plus y squared minus 12y, and then 4 goes into there. 144 divided by 4 is 36 dy. And of course, this is about as good as it gets. The y squareds will cancel. The 12y is going to cancel. And the only term left on the inside is that 36. Square root of 36 is 6. So if we factor out that 6, we have 12 pi what is the integral from 2 to 10 of dy? 8. It's the length of the interval. So that 6 factors out. If you integrate dy from 2 to 10, you get 10 minus 2, which is 8. So that'll be how it simplifies down. Again, no one step is that difficult, but there's a bunch of little steps that you've got to sort of keep track of. All the algebra, combining square roots. Any questions on any of the steps? Yep.
Mathematically, why do the square roots cancel out when we multiply the square root of 12y minus y squared to like the 1? Why do we get rid of one of those square roots?
So we're not getting rid of a square root, we're combining 2 square roots into 1.
Which you can do because they're multiplying.
So if we have something, if we look at a much simpler scenario, let's suppose we have something like this. The idea is that the square root of a times the square root of 1 plus b turns into 1 square root where you take the inside here and you multiply it to the inside of the second one. And so it's not that there's a square root that's disappearing, it's that the 2 square roots are combining into 1. So when we do that here, we have the square root of this and the square root of that. The 2 square roots are turning into 1 big square root, and then whatever's inside here gets multiplied by whatever's inside here, so it gets distributed to this and distributed to that. Does that make sense? So the product of roots is a square root of products. Right, so we're just forming the product of the insides. But there is only 1 square root in the end. Which also kind of reminds you of this, but like if we have the square root of 5 times the square root of 5, we know that here the square root disappears because the insides match. You know, if we wanted to, we could think of it as the square root of 5 times 5, which is the square root of 25. So that's why the square root disappears, because these match. But in this case, the insides obviously don't match, so we have to keep the 1 square root of the product of the insides.
Okay, that makes sense.
All right, let's do one last one. And then we'll get to our physical applications. The places where we really do use the math. Word problems. But we all hate doing word problems, even though you hear it all the time. Well, where are we going to use this? With word problems. But I don't like word problems. Yeah, well, that's the question. All right, here we go. We have a function here. It's part of a circle. Let's see. So we've got this circle up here of radius 10, but we're only considering part of the upper semicircle from -8 to 8 that's rotated around the x-axis. And we want to find the surface area of that surface of revolution, but then they are telling us that we're going to paint it, so what's the volume of paint? Well, the math that we really are interested in is finding the area of this surface. The volume of paint is just found by multiplying that area by whatever the thickness of the paint is. And so they tell us that the paint is going to be 1.5 millimeters thick. We're going to convert that over to meters. So the meters of surface area times the meters thickness will give us the cubic meters, or the volume of paint that we're going to need. So the main thing here is that we've got this upper semicircular-ish, we're not dealing with the whole semicircle, part of the upper semicircle. And if we're dealing with an upper semicircle, we have to isolate y from this equation. So we're choosing the positive square root because we want the upper semicircle. So that is our function. Now the way this is set up, we've isolated y, which is measuring vertical, so that's matching. If we rotate around the x-axis, and we choose a point element on this curve, this point element right there is rotating around the x-axis, creating a circumference. The radius of that circumference is this vertical distance. The function is presented as measuring vertical distances, so everything is copacetic right now. It's all lined up as we would like it to be. We know that this ds here is going to involve a 1 plus the derivative squared. So let's go ahead and find the derivative here. So the derivative power is 1/2, so we bring down the 1/2. We subtract 1 from the exponent. And then we multiply by the derivative of the inside. We have a little tiny bit of cancellation here. The 2 in the denominator can cancel with this 2 in the numerator. And then we are going to square this because we know that in the ds there is a derivative squared. The numerator only has a negative x in it, and when that's squared it becomes an x squared. The denominator has the square root of this. When we square that, the square root goes away. So that denominator has a square root of 100 minus x squared. That squared gives us 100 minus x squared. So now we can go ahead and find our surface area. That's going to be the integral from, let's see, we definitely can use some symmetry here. So the interval that we're integrating, it tells us that we want to go from -8 to 8. So there's -8, and we're coming all the way across to 8. But we could go 0 to 8 and double it. If we go 0 to 8, we will definitely be getting exactly half of the surface area. Whenever we can introduce a 0 as a limit of integration, that's generally a good strategy. So let's go ahead and put a 2 out in front. So this is by symmetry. And we'll go 0 to 8. And then we have the 2 pi r. R is the function. And then we have the ds, which is 1 plus the derivative squared. We found the derivative squared. So there's our setup. And the inside then of this square root is going to be distributed to the inside over here. So it's going to be multiplied to the 1 and then multiplied by that fraction. So very similar setup with all of these surface area ones. We'll have 4 pi integral 0 to 8. 1 square root, so 2 square roots become 1. Multiply 2 square roots together, it becomes 1 square root. The inside of the left one multiplied by 1. So this yellow is being distributed there, and then it's being distributed to the fraction. And when it's distributed to the fraction, it cancels with the denominator that's in that fraction, so what's left?
X squared.
X squared, just that numerator. So this is also nicely cooked up. So we'll end up with 4 times pi integral 0 to 8. These are canceling. So we take the square root of 100, get 10. So we get that. So this will be 40 pi multiplied by what? 8. The integral from 0 to 8 of dx is the length of the interval, which is 8 minus 0, which is 8. So we multiply by 8. So we get 320 multiplied by pi. Any mysteries?
Now do we multiply that for the Okay.
So that is our surface area, and the word problem said, what is the volume of paint that we're going to need? So we've now found the area of this surface, so then we'll multiply that by 0.0015. So that'll give us the final answer for what they're asking for. That multiplied by 0.0015, and this will be cubic meters. And they didn't say up here what to round to. So whatever, like on a homework problem or a test question or a quiz question, it would tell us what to round to. So we would just type all that into our calculator and round appropriately. Or we could do the 0.0015 times 320 and leave the pi in there if they wanted it to be exact. So remember that exact means leave the pi, leave the square root of 2, so that it's not only approximate if it asks to approximate. Otherwise, you leave the pi, leave the square root of 2, or all that stuff. All right. So, our last section in this chapter, 6.7, is the physical applications. The physical applications in Calc 2 and in Calc 3, 90% of them are physics applications. So hopefully, has anyone had no physics whatsoever in here? So if you've had no physics, you may have to do a little bit of YouTubing or whatever, just if you're not familiar with some of the concepts. We'll talk about them from scratch, but you might need to do just a little digging just to make sure that you're understanding some of the ideas behind. We're going to be talking about work. We're going to be talking about force. We're going to be talking about work, force, mostly work and force. Oh, I guess mass. Mass is the other thing. Mass, work, and force. So, and one of the topics when we're talking about force, it's really helpful to understand hydrostatic pressure. So these weekly videos that there's no homework on, they're just interesting. These two on pressure, on hydrostatic pressure, will be really helpful. Very helpful to get a sense of what hydrostatic pressure is. The thing that's interesting about hydrostatic pressure is that when you're in water, water pushes in all directions with equal force. Right? It's pushing up, it's pushing down, it's pushing sideways. So, like when you're standing at the bottom of a pool, you're feeling pressure from all directions. So so watching those would be helpful to get a better sense of hydrostatic pressure. Okay, so let's talk about the simplest scenario with mass. If we have some solid object and the density is uniform, in other words, the density at every single point in that object is the same, so it's got uniform density, then it's really easy to find the mass. If you're given the density and you know the volume, you just form that product. One way to sort of rewrite this, if this doesn't feel good to you, some people prefer to think of density as the mass per unit volume. So you could write density equals mass divided by volume. That's another way. For some people, that's easier to remember, and then you could write mass by multiplying by the volume. Whatever works for you in terms of getting that formula down. Mass is density times volume. You can think of volume as mass. You can think of density as mass per unit volume, and then rewrite it. Whatever works for you. Now, of course, if you're in calculus, the density most of the time is not going to be uniform. So if the density is varying, that means that we have a different density at each point. Well, then mass is not just this product if density changes, depending on where you are in the object. And the way we get at finding mass with a variable density is to integrate the density function throughout the object. If you're dealing with a solid object, that will require a triple integral, which you will do in Calculus 3. So in physics, we think of 3 different types of density. We think about one-dimensional density, so like the density along a wire or a very thin metal bar. You can think about the density of a flat object, which they usually call a lamina, like a sheet of metal. Then you're talking about 2-dimensional density. And then in volume, you're thinking about 3-dimensional density. So we've got to kind of know what the context is. This is the most natural idea of density, is dealing with volume. But if we are in the 1-dimensional density case, so right here, then we are thinking of the following. So in 1 dimension, we are thinking of mass per unit length as opposed to mass per unit volume. In the 2-dimensional case, so like a sheet of metal, density will have units of mass per area. And then in the 3-dimensional case, you will have mass per unit volume. So it's a little, you've got to be a little careful. You need to know what dimension you're dealing with. In this class, we are going to be dealing with 1-dimensional, because if your density varies, in this case you would need to use a double integral to build up to mass, and in this case you would need a triple integral to build up to mass. So you'll do these 2 cases in Calc 3. So for us, we're imagining a wire. If we want to get to the mass and the density is varying along that wire, all we have to do is integrate the density and we'll get to mass. So for us, we're looking at the simplest case, and that simplest case is going to be just integrating the density function. So here we're dealing with a thin little bar, a thin metal bar. We've got this density function there, and we're looking on the interval 0 to 1. All we do is integrate it. There will not be a test question to find the mass of a bar in 1 dimension. This is just more of a building block for where we're going. But the concept is going to be the important part. If you integrate density, you get to mass. So all we would do in this context is integrate with respect to x. 0 is not contributing, so we'd have 1 plus 1/4, so we'd end up with 5/4. And then if we're using the traditional metric units, what would be the units of mass?
Grams.
So if we're going with the standard metric, we would go kilograms and meters. So we would use kilograms as our unit of mass. They didn't tell us that that's what was happening here. They didn't give us units, but most of the time when we're dealing with these concepts like work and force and mass, we're going to be using kilograms and meters. Those are the standard units that we would use. Because acceleration is given in meters. And
Should we write units like on the example?
only if it gives you units. Only if it gives you units. If I don't give you units and we're dealing with one of these, no. When we get to work and force, we will want units though, because they'll be given in the problem every time. We'll be dealing with emptying a tank that has water in it, and the density of water is 1,000 kilograms per unit of volume, whatever we're using. So yeah, and those ones we'll definitely use them. But here they didn't give us units, we don't really need them. This is more just sort of a reminder that if we're measuring mass, it's usually kilograms. And same idea here. We are going to simply integrate the density function on the interval, and that'll give it to us. So, antiderivative for that exponential function. Certainly the 5 comes, and then itself. So if we integrate an exponential, we always get itself. And then what do we do?
Divide by
Divide by -2. because this is a linear exponent. So you could use substitution, but we've seen that if your substitution happens to be linear, you can cut to the chase by dividing by the derivative of that substitution. So we would have that. Okay, so this is going to give us negative 5 over 2 multiplied by e to the negative 8 minus e to the 0, which is 1. So that, again, is measuring mass, which we're assuming would be kilograms. Obviously, you could have special cases where you are finding grams, but whatever. Is there anything weird about that answer for kilograms? Is that a positive number? Certainly negative 5 halves is negative.
I think it would be multiplied, both sides are going to be negative, so.
Both factors will be negative,
Yeah.
right? So this e to the negative 8, super teeny, subtracting 1, this is in fact negative, right? So we do have mass, we do have a positive number, which is what we would need if we're measuring mass. So just note that that is, may not look like this is positive, but this factor is negative, that factor is negative, so we do get a positive number. So it does, it passes the sniff test, that we're on the right track. Okay, so let's go ahead and get to the next application. Oh, didn't mean to do that. We want to go to the concept of work, and we're going to move to the spring. That's always the first sort of problem that you ever deal with when you're finding work. So the concept of work, in the simplest case, where you apply a constant force to, say, a block or a wagon or whatever. You're pushing with a constant force. If you are pushing with a constant force, work is nothing more than the magnitude of that force times distance. So work is force times distance. Okay, but of course, we're in calculus and the force is not going to be constant in most cases. The only case we see where this force is constant is if we grab a block and we lift a block. If we lift a block, that's going to be a constant force, and we can find the work done by multiplying mass times gravity times distance. So we'll get to that though. So typically force is variable. So they've shown us a scenario here. We've got a force that's a variable force. That force varies as we're moving through time. And if we have a variable force, then we have to go back to the Riemann sum idea. And the idea is that we are going to break up our interval. So wherever the block is moving, the interval is moving. The interval is, say, A to B. We're going to subdivide the interval. And there's going to be a little work done on each subinterval. And on a small subinterval, you can imagine the force is almost constant if you get down to a narrow enough interval. So we're going to have all of these tiny works formed by the force on that subinterval times the width of that subinterval. And then we add them all up. It's a Riemann sum. Take the limit of the Riemann sum. Abracadabra. The Riemann sum turns into what you learned in Calc 1, the definite interval. So, moral of the story is, if we want to find the work done, we integrate the force. That's what we're going to do. Integrate the force. Now, force and work can both be negative. So we'll come across some scenarios. The main idea is if the force is in the direction of motion. So for there to be work done, the object must be displaced. It needs to move. And if the force is in the direction of motion, work will be positive. So if you imagine driving your car, when you're slowing down, the work is going to be negative because you're moving forward and you're applying the brakes. That force is in the opposite direction. So the work in slowing down is in the opposite, is a negative number. Okay, but in general, if the force is in the direction of the motion, then you're going to have positive work. Okay, so we integrate force to get work. That is our main thing. With a spring, we imagine these springs horizontal for now. And the spring at equilibrium, we're going to call that the origin right there, where the end of the spring is. And if you stretch the spring, if you move it in the positive direction, if you stretch it, that's going to be a positive force. If you compress it, it's going to be a negative force. Okay? So, how about the work in both those cases? Is the work positive in one and negative in the other, positive in both, negative in both? So the tip of the spring here is moving in that direction, which is the direction that the force is being applied. So the force and the direction of motion are the same, so that's positive work. Here, we're compressing, but the force is to the left, and that front end of the spring is moving to the left, so that's also positive work. Because the motion is in the direction, the force is in the direction of the motion. So both are positive. Now the reason we start with springs anytime we're dealing with force problems is that springs satisfy Hooke's law, which is super simple. The force is directly proportional to the displacement. You all have experienced this. The tighter the spring gets, the harder it is to move the next inch. Same thing with stretching it. You stretch it a couple inches, each inch it's harder and harder to stretch it. But it's linear. It's not some crazy function. It's just a linear function, which is kind of cool, that it's that simple. All right, so here, with Hooke's law, we need to know what this K value is. So that's called the spring constant. And every spring has its own constant depending on how much resistance it has, how much force it takes to move, to compress or stretch the spring. So it's kind of like in college algebra, you do those radioactive isotopes. Every radioactive isotope has its own decay constant. Same idea. Every spring has its own spring constant. So we have to find that spring constant by using some initial value. Same thing you did in college algebra with the radioactive isotopes, with the half-life. The half-life of an isotope was whatever it was. You plugged those in and you figured out what the K value was. Same idea here. So they tell us that it's going to take a force of 15 newtons to stretch and hold the spring 0.25 from equilibrium. So that tells us this following data point. So the force is 15 newtons. We don't know what K is. And that 15 newtons force is what it takes to displace it 1/4 of a meter. They could have also used the word compress. Wouldn't matter. The K would still be the same. If it compressed, the displacement is 1/4, and we would still get the same spring constant. So we're going to get 60. 60? I said 60. I didn't write 60. So we're going to get 60 when we multiply both sides by 4. So that is the spring constant. So for this spring, the force function is 60 times x. So that's the force function for this particular spring. So this is part A. We found the spring constant. That's our force function. How much work is required to compress the spring 0.2 meters from equilibrium? So we want to find the work. Well, we're going to integrate the force function. There's our force function. And it says from equilibrium, so we're starting at 0, we want to compress it 0.2 meters. So what should that upper limit of integration be if we're compressing?
1/5.
So we're going to go to 1/5, but we're compressing.
So 4/5? Oh, I guess it doesn't make sense.
negative 1. If we're compressing, we're moving in the negative direction, so we're going to move to the left of the origin, as opposed to stretching, we're going to move to the right of the origin. So if we wanted to be, spot on here, we would say that this is going to be 1/5 with a negative sign. Now, will it matter? Could we have sort of said, well, by symmetry, we could have made that a positive 1/5? Could we do that? Let's see. Let's just look at the math. When we integrate here, don't we end up with a quadratic? So when we integrate, we see that we get a square, and we realize, oh gosh, yeah, it's not going to matter if we compressed it by 0.2 meters or stretched it by 0.2 meters. It takes the same work. The spring is symmetric, right? It's a linear function, so it's going to be symmetric in terms of whether you compress or whether you stretch. And mathematically, we see why that is. The antiderivative here is a quadratic. Doesn't matter if we plug in a positive or a negative. So we're going to end up with 30 multiplied by 1/25. So we're going to get 6/5. And then our units here, so we're dealing with meters and newtons. So work is going to be a Newton meter. So force times distance. Force times distance gives you work. And what's the other word for a Newton meter? Newton meter is also known as a joule. So a joule is just another unit of measure. It means the same thing as a Newton meter. I don't care if you write it as Newton meter or write it as joule. It does not matter. So either way is completely fine. So 6/5 Newton meter. Okay.
So,
Yep.
can I ask, mathematically here, we're saying, due to the fact of that square root, it would take the same amount of force to move it by compressing and stretching?
Yep.
Is that something that is normal for springs? Or?
Yes.
Okay.
So for all springs, whether you're compressing or stretching, same work to go the same distance.
Okay.
Yep, they are symmetric. And the more interesting thing about these springs is that it's linear. Doesn't it feel like it should probably be exponential or something that's not quite so simple as just linear? It doesn't, obviously the math has been done and it's linear, but it just feels kind of counterintuitive that a spring is only linear. I mean, it feels like it gets hard real fast, whether you're compressing or stretching. Okay, part C says how much additional work is required to stretch the spring 0.3 meters if it has already been stretched 0.25 meters from its equilibrium position. So in other words, the spring is starting at 0.25 and we want to go an additional 0.3. So this would be the setup here. So if we are only, it's not asking us how much work is done in stretching at 0.25. It's saying how much additional work is required to stretch the spring 0.3 meters if it's already at the 0.25 position. So we want the additional work. So we'll get the same antiderivative, 30x squared. And the best approach, they didn't say to approximate here. If it doesn't say to approximate, it's always best to use fractions so that you're not dealing with decimals. And this would be 55 over 100, so 11 over 20. And so whatever this ends up being, we would take that and make that 121 over 400 minus 1 over 16. And whatever that simplifies to. And again, that will be units of Newton meters or joules, either one. I don't care which one you use. But if it doesn't say to approximate, we should leave that final answer as a fraction. You don't want to type it in and get a decimal. One of the nicest features of our modern calculators is turning decimals into fractions. And Desmos, that's so convenient. Okay, so the spring, let's do one more spring one. So calculate the work required to stretch the following springs 0.4 meters from their equilibrium position. Assume Hooke's law is obeyed. So why don't you all do part A? So the spring that requires, so here they're giving us some value that can be used to find K. All right, so they tell us that we need a force of 50 newtons to stretch it 1/10 of a meter from equilibrium. So that's our data point that can be used to calculate the K value, the spring constant for that first one. So find that spring constant and then answer this question. And we want to stretch it 0.4 from equilibrium. Maybe I'll do some roll while you're working on that. Mohammed? Gael? Andre? Oh, Grace is not here. Where is it? Marcus? Ethan? Sean? Maximus? Hayden is not here. Ann? Alexander? Che? Caitlin? Stockton? Oh, Nathan is here. Mason? Maxwell? Caleb is not here. Sebastian is not here. Garrett? Garrett? No Garrett. Saxon here. Tura. Normally there. Well, have some people. Eric is here. Jesse. Yep. And Will. Tyson. And Milan. Did I see you? There you are. Yeah. What do you all get for your K?
500.
So to find that K is pretty straightforward when we're given both the F and the X. So we're told that, oh, it's going to take 50 newtons to stretch it 1/10 of a meter. We get that our K is equal to 500. Is that what I heard? Yeah, 500, okay. And then it says that we want to go from equilibrium, so our force, we're going to integrate from 0. We're stretching it, so we use a positive 4/10 or 2/5. And then we use our force function, which will be 500x. So there's our setup for the work part of part A. That'll give us 250 multiplied by x squared from 0 to 2/5, which will give us 250 multiplied by 4 over 25, which looks like 40 joules of work. Make sense? Not too bad. Now the second one is a little different. So again, in order to get your spring constant, you need a data point. And notice that the data point they give us is a little different. The traditional data point is giving us newtons and meters, but notice that they gave us the work necessary, the work done in stretching at 0.1 from equilibrium. So they're not giving us F and X, so we can't use that equation. They're giving us the work that it takes. So the work in going from 0 to 1/10 of a meter will look like that. We don't know the K, but we do know the work. They're saying it's going to take 2 joules of work to stretch it 1/10 of a meter. So notice that they've sort of given us an indirect way to get to k. We can solve this by integrating, and then we're going from 0 to a 10th. Okay. The only unknown is k, right? That x is dummy. That x is going away as soon as we plug in our limits of integration. So that x will be gone. So I'm going to multiply both sides here by 4. Multiply both sides by 2 to get a 4 on the left. And then x squared, when we plug in a tenth, will be a hundredth. And so this tells us that k will be 400. So a slightly different way to get at that k value. And then they asked us again to find the work from 0 to 2/5. So we're still going to set this part up, 0 to 2/5. And our force function will be 400 multiplied by x. So this will be 200 x squared from 0 to 2/5, which will be 200 multiplied by 4/25, which will be 32 joules. Any part of that you want to ask about? So when you get into your physics classes, that'll be usually the first work problem you do is dealing with these springs. And for the most part, it's pretty basic logic, and there's a lot of symmetry, so you can often get away with making everything positive and not dealing with compression ever because of the symmetry. And not having to think of a negative force, creating a negative work and those kind of things. All right, let's go ahead and I think we should probably take our 10-minute break right now before we start on this more complicated stuff that involves pumping and lifting and all that stuff. So let's take our 10-minute break, and then we'll get into the weeds with the harder applications. But we are going to be finding work done in draining a tank. Or, so you can think of it as draining the tank out the bottom, or you can think of it as pumping the water out of the top of the tank. In either case, work will be done. If you're pumping water out of the top of the tank, work is done by the pump. If you're just pulling out a plug at the bottom of the tank, the work is done by gravity. Sometimes those works will be equal. If you have a cylindrical tank or a rectangular tank, so that essentially the top half geometrically matches the bottom half, the work done whether you pump it out the top or out the bottom, it's going to be the same. If you have a non-symmetric tank, and by non-symmetric I mean the top half is different than the bottom half, like a cone, the work will be totally different whether you drain it out the bottom or pump it out the top. Or if you have a trough or something. So the only way the work is the same typically is a cylindrical tank or a rectangular tank. Otherwise the works will be different. And the reason is that the distance traveled by each cross-section of water changes, right? So if we have a cylindrical tank, each cross-section match it, right? The cross-sections are all the same. And so there'll be just as many cross-sections going the full distance, whether you're going out the top or going out the bottom. But if you have a cone, the cross-sections don't match, right? You have bigger cross-sections if the cone is this direction. And so the cross-sections won't match. So you'll have different works. So let's talk about, first off, the block situation. So by the block situation, I mean this, that when we're dealing with work in its simplest form, where we've got that constant force and a constant distance. So like if you imagine a block and you're just lifting it up, you can think of that block as a point mass. And so you've got that constant mass and you're just going to lift it. The force, Newton's law, says that force is mass times gravity. And so if we're lifting a block, all we have to do is mgh, mass times gravity times height or distance traveled. So mgh, mgy, however you want to think about it. So that's the simplest case. Now, with the tanks, we don't have that simple case anymore. The force is going to be variable because the cross sections, because we have all these cross sections that have variable area. And they're moving different distances too. So distance is a variable too. Like the cross section right here is going to move further than the cross section right here if we're pumping out the top. It also has a different area. So if it has a different area, it's got a different weight. So different force. All right, so there's the integral. It looks terrible. It is terrible. We need to come up with a way to create this integrand in an easy to remember way. We need an acronym that is going to make this as simple as possible. So they talk about this rho, that's density. Density of whatever fluid is being pumped or drained. G is gravity, so that's acceleration due to gravity, 9.8 if we're dealing with metric system. A of y is the cross-sectional area. So if we're dealing with this cylindrical, this parabolic tank, each cross-section is a circle. So that area would be a pi r squared. That d there is the distance traveled by your cross-section of whatever the fluid is. So let's first just glance at the units, and then I'll give you, I think, a pretty easy way to remember all this. So there are all the things in there. And we know that force is mass times gravity, mass times acceleration, ma, so mass times gravity. Here is the gravity, right there. And first off, notice that this is a distance thing right there, and that's a distance factor right there. dy is a tiny change in distance, so it has units of meters. D of y is the distance traveled by your cross-section, so it also has units of meters. And with an integral, you can kind of think of the unit. It doesn't matter how you compile the units. Like if we want to create volume, volume is area times distance. Right? Area is meters squared, and if we multiply that by distance, we get meters cubed, which is volume. Now, the best way to think of getting your volume is with this area and this unit of length. But it doesn't really matter. dy and d of y both have units of length. So we don't have to think of it that way. That's the way I'm going to encourage it later. But just in matching these units, if we look at all that, that will have units of volume. Area times distance is meters cubed. So now we have density multiplied by volume, and density multiplied by volume is mass, and then mass times gravity, right there, that is going to give us force. So then we are going to have force integrated with respect to y. Force times distance is work. So if you look at the entire integrand, including the differential, you will end up with units of work. Or your other perspective is that if you integrate force, you get work. So this right here will be units of force. And then you'll get work. Integrate force to get work. Now, how do we memorize all this stuff? Well, we memorize it this way. We need an acronym. And this acronym, to me, works beautifully. So if you do a little bit of rearranging, this is how I'm going to encourage you to remember the work formula. ADD, it's a math word, super easy to remember, times volume. A is acceleration due to gravity. D is density. Second D is distance. ADD, acceleration, density, distance. And the volume I put in parentheses because that volume is measuring the volume of a slice. So we've been dealing with slices already. Remember, a cross-section is two-dimensional, but a slice has 3 dimensions. Got a little thickness to it. And so that volume in parentheses, what I mean is the volume of a slice. Not the volume of the tank. It's the volume of a slice. So it includes the dy, which is the thickness that you attach to your cross-section that's two-dimensional. You've got your cross-section that's two-dimensional. You multiply it by dy. You've now created a slice, which is a little volume. You have a tiny, disc-like a volume. So ADD volume is going to be for work. And then in a moment, we're also going to be dealing with force. And force is going to be very similar. It's going to be ADD area. And this will be when we're finding the force on a wall where water or whatever fluid is pushing on a wall, and we want to find the cumulative force on that wall. We need to find force. We'll see that it's ADD area. We'll get to that in a minute. Notice that the only difference between these two is that we're missing 1 unit of distance down here. If we were to multiply force times distance, we would get to work. So if we take force and multiply it by distance, we will get to work. If we take area and multiply it by another unit of distance, we would go from area to volume. All right, so this is the one we're starting with, and if we just sort of peel off one of the units of length, we'll end up with force. Okay, force times distance gives us work. Now this book starts with these examples that deal with ropes and chains. I want to do those after we actually do the draining of the vessels. The draining of the vessels is more intuitive. Sometimes a case that seems simpler is actually harder because there's some things missing. And you kind of need to know why something is not there. So we're going to come back and do these slightly out of order. Let's do the vessel draining first. So I'm going to skip these 3 slides for a second. And let's go to the simplest draining vessel problem. So here, simplest one, it's symmetric vertically. The top half and the bottom half are the same. The work would be the same whether we pull the plug and drain it out the bottom or pump it out the top. The work would be the same. The work's either done by gravity if you drain it out the bottom, or it's done by the pump if you pump it out the top. Okay, so let's first start by looking at a representative cross-section. So we've already been doing this kind of thing when we found volumes. We took a cross-section. So there's a representative cross-section. That representative cross-section, it's horizontal. It's at a random y value. So that y value is measuring its distance. So we think of the coordinate system in the same way. Up is positive. So the floor of that cylinder is at y equals 0. The height of this cross-section is at y, so that distance is y. What does that make this distance then, from there to there? If this tank is 8 meters tall, what would that upper distance be right here?
8 minus 1.
8 minus y, right? If y is that distance right there, then this green distance is the complementary distance. If this is y, and that's 8 up there, then this part is 8 minus y, that complementary distance. Okay, so here we're going to imagine we're pumping out the top right here, so we're pumping it just over the top. So the exit point is right at the top. So here's what I would recommend. We want work. That's going to be the integral of ADD volume. We want work, ADD volume. So here are the pieces. We have cross-sections of water from 0 to 8. So each cross-section of water needs to travel out the top of the tank. There's our representative cross-section there. If we want to turn this representative cross-section into a slice, we have to add dy to it, right? I say add, you know what I mean, multiply by dy, the area of that cross-section times dy gives us the volume of a slice. Okay? So, acceleration due to gravity, 9.8. Density of your fluid. Oh, we're dealing with water. Water is 1,000 kgs per meter cubed. So 1,000. Second D is distance traveled by that cross section at your representative height of y. That distance traveled is 8 minus y if we're draining out the top. If we were just draining it out the bottom, what would the distance traveled by the cross section at height y be? Y. Right? It would have to travel y to get out the bottom. So if you replace this with just y, because this tank is symmetric in this vertical way, you will get the exact same answer if you replace that 8 minus y with a y. It'll be the same. You will get the same exact answer. So there's the ADD part. So ADD, acceleration, density, distance. ADD. Now the volume. Again, the volume is not the volume of the tank. It is the volume of our representative slice, which is the area of the cross-section multiplied by dy. So dy is going to give us this dimension, this vertical dimension right there. So the volume is the volume of that slice. The volume of that slice is the area of that slice multiplied by dy. So this right here is area, which makes this whole thing volume, which is why I put it in parentheses to sort of emphasize that you're including the dy. So it's not like big volume, it's a tiny volume. It's an element of volume. So what's the area of every single cross-section?
2 pi.
So pi r squared. Pi r squared, the radius is 2, so we end up with what for every single cross-section?
4 pi.
4 pi. Right? 2 is the radius of each of those cross-sectional disks. The area of a disk is pi times the radius squared. The radius is 2, so we get pi times 2 squared. So remember that dy is part of that volume. That's the volume of our slice. We now pop all these constants to the front. The 9.8 times 1,000 is 9,800. 4 pi is a constant. That can come to the front. We have 0 to 8. 8 less y. We have that. That's the hard part. Now we just have to integrate. So we have to make sure we understand that. So if you can get this acronym down, these things actually are not that hard. If you can remember the acronym, ADD volume, and know what each of the pieces means, you will be good to go. All right, so let's just leave these constants out in front for a minute. Maybe some cancellation will occur, who knows? So this will be 8y minus y squared over 2, from 0 to 8. Plugging in 0 contributes no work. Plugging in the 8. We're going to have 64 minus 32. 64 minus 32 is 32. So whatever this multiplies by, maybe someone can multiply that out for us. So that'll be, and we'll leave the pi in there, unless it says to approximate, we'll just leave the pi in there. So how many joules do we end up with? 128 times 9800. you say one, is that what you said?
Yeah.
Okay, thank you. So somebody confirm.
Got the same.
Got the same thing, perfect. All right, so that is our process. These problems aren't that long. ADD volume, just plug and chug. This is the simplest one, the cylinder. Let's up the ante a little bit. Up the ante. Okay, to a horrible trough. Okay, so this trough, oh, let me point out one thing that I want you to keep in mind. So what if, let's just suppose we were told that there was like a pipe up here at the top, and we were going to pump it out this pipe instead of right over the lid. Instead of going right over the top, let's suppose that this was a 3 meter pipe up here. So instead of pumping it right out the top, we have to go 3 meters above and then pump it out. What would change in this right there? What would change? Distance traveled is the only thing that would change. Limits of integration reflect the physical location of the water. We still have water 0 to 8. That's not changing. The only thing that would change is right here. Instead of our distance being 8 minus y, it would have to travel all the way up to here for this representative slice. So what would that distance be? 11 minus y. So that would be the only change if we weren't pumping it right out the top. Limits of integration stay the same. Everything else stays the same. It's just that that cross-section of water has to now travel a little bit further. It has to travel exactly 3 meters further than in the prior setup. So we have to add 3. So that's the only thing that would change. All right, so let's manage the trough. So there's our trough. We need a horizontal cross-section. So our horizontal cross-section is going to come right across here, and then it's going to be the length of the trough, and then it's going to also be on the back, right there. So there is our cross-section. That's what our cross-section is. In order to do this, let's draw the face of the trough. And let's do our horizontal cross-section. Let's suppose it's green, so there to there. There is the face of our trough. That's going to be this front edge of our cross-section. That's a horizontal distance. We are going to need to know the distance across that semicircle. If we're going to find the distance across that semicircle, we need the equation for that semicircle. There are multiple ways to do this. I always will do these things in a way that the trough is sitting on the ground there. I'm going to create the coordinate system so the circle or semicircle is sitting on the ground. You could set your coordinate system up to be like this. Ooh. You could set it up there where your x-axis is there. In my mind, that makes it a little more complicated because your limits of integration are going from a negative number up to 0. So I prefer to do it the way I'm about to do it. You can do it that way, though. So I'm imagining this scenario right here. Right there. So we have a horizontal cross-section at y. Now, the center of our semicircle, or circle if you imagine the whole curve there, the radius is 1/4. So we know that we have x squared plus y minus 1/4 squared equals 1/4 squared. Let's make sure you agree with that. So this circle, the x coordinate is not shifted in any way. If we had the circle centered at the origin, the x value is the same as it is if it's shifted up or down. But when we shift it up, because the radius of that circle is 1/4, the center of the circle, if it was at the origin, it's now shifted up 1/4 unit, so the center is 0, 1/4. The radius is 1/4, which is right there. What letter do I need to solve for, x or y? X. That green segment is horizontal, so we need to solve for x so that this curve is measuring horizontal distances. So we're going to isolate the x. So we have x squared equals, let's make this 1/16 minus y minus a quarter squared. And if we take the positive square root, and then inside here I'm going to FOIL this out, so we have y squared minus, we know this is going to be a plus 1/16 over here. So we're doing the a minus b squared thing. So the middle term is going to be negative. We do a times b times 2. 1/4 times y times 2 is 1/2 y. So this is going to be the right half of the circle. The 16ths cancel. So that equation right there is the equation of that. And it's only measuring from there to there, correct? It's not measuring the full width. That, when you solve for x, it's only measuring from the y-axis over. So if we call this full distance across w, so w goes all the way across, w will be that multiplied by 2. So this will be the width of our cross section. Does that make sense to everybody?
Yeah.
This x value is only measuring from the y-axis over. But we have to double it to get all the way across that parabola, or that semicircle.
So in our original circle equation at the top, x squared plus, why does the y being subtracted by 1/4?
Because it shifted up a quarter of a unit. So if we look at this equation right here, let's pick one with no fractions. Fractions make everything hard. So if we have a circle of radius 2, that's the equation.
Okay.
If we are going to shift it, let's suppose we shift it up 2. So we're going to shift it to there. This distance represents the shift. So this would be x squared plus y minus 2 squared equals 4. Let's notice that if you plug in y equals 2, what do you end up, like,
Yeah.
what do you get?
0 if you plug in y.
So if you plug in y equals 2, you get 0 there. So you get x equals plus or minus 2, which is representing the x coordinates right there and there.
Okay.
So if you plugged in 2 for your y value, you would get those two.
So you were just raising it?
Yep.
Okay.
So instead of having the circle be below the x-axis, where your limits of integration in this context would be from -2 up to 0, I'd rather have the limits of integration be positive numbers.
Okay.
So I'd rather shift the circle and deal with that than deal with negative limits of integration. But you could. You could.
Thank you.
Okay, so there's our width. Now let's go ahead and set up our work integral. So again, for work, we're going to integrate ADD volume. Volume is not the volume of the tank or the trough. It's the volume of a slice, which is a cross-sectional area times dy. All right, so we will have, once again, acceleration due to gravity, 9.8. Once again, water density is 1,000. Those are almost always the same. Now we have to figure out if the water is being pumped right out the top here. So here's where the water is exiting, right there. What is this distance that the cross-section at height y travels?
Quarter of a meter.
Quarter minus y. Right, because the radius of this circle is 1/4, so that distance is a quarter. So then we have to subtract off y. So the distance it will travel is 1/4 minus y. And if a quarter is the full distance, and y is that partial height, then the complementary height is a quarter minus y. It's going to be the height that's left. So a quarter minus y is going to plop in right here. So now we have the ADD done. And the limits of integration are 0 to a quarter. Because it's a circle of radius 1/4. Okay, so there's the ADD. Now we need the volume of a slice, our representative slice. Well, the volume of our representative slice is going to be the area of the cross-sectional area of the cross-section multiplied by dy. So volume, let's see. It's a rectangle. So the area of a rectangle is the product of the two dimensions. Well, the dimension across the front is the width. So that's going to be 2 multiplied by this root, multiplied by 3. This is the area of the cross section at y. So that is the area. And then how do we get thickness? dy. This whole thing, if we include the dy, is now volume of slice. So area of cross-section multiplied by thickness multiplied by dy, that gives us volume of a representative slice. Now we have it. All the constants, the multiplicative constants can come to the front. We've got a 9800 like we often will from those two. And then it looks like we have a 6 from in here to the front. So we have this integral from 0 to a quarter. And let's see what's left inside. 1/4 minus y multiplied by this square root. We've got that. All right. If this gnarly looking integrand, which is a product, if that was going to be integrable, there's only one technique that we have at this stage that could possibly work, and that is?
Reverse chain rule?
Reverse chain rule would only be if the substitution were linear. What would the substitution be if we were going to do substitution here? So if we do u substitution, we would want to let u be what's in the square root. But that's only going to work if its derivative is on the outside of the square root. Let's check and see. Is it? So this is the natural choice for substitution, is whatever is, in an exponent, in an angle, in a square root. It's something that's buried inside of a function. Let's see. Derivative here, we would get negative 2y plus 1/2 multiplied by dy. Almost. Almost. If we divide both sides by 2 here, we divide both sides by 2, we get negative y plus 1/4 times dy. And that's it. Right, that's what we have in front. A quarter minus y, commutative law of addition. We could write this as a quarter minus y or minus y plus a quarter. Those are the same. So those match. That means the substitution will work because its derivative matches what's on the outside. So let's try it then. Maybe we'll get some cancellation, not multiply this out quite yet. So the integral, we get a u to the 1/2. So u is the inside of the root, so we have u to the 1/2. And then this whole piece right here, 1/4 minus y times dy, that's all this. So that all gets replaced with du divided by 2. So there's the du. And divided by 2 is a constant. We'll just factor it to the front. So substitution looks very nice here. How about limits of integration? Okay. So we come over to this equation where we related u and y. If y is 0, u is also 0. How about if y is 1/4? If we plug in 1/4 here, we will get negative 1/16 plus 1/8. Negative 1/16 plus 1/8 is 1/16. Right? 2/16 make up an eighth. If we subtract off 1/16, we're left with a 16th. So we will be right there. Okay. So this is going to give us 9,800 times 3, canceling out a factor of 2. This is going to be u to the 3/2, adding 1 and dividing by the new exponent, and our limits of integration will be 0 to a 16th. Close. Close. Almost made it. So add 1 to the exponent, divide by the new exponent. We have a little more cancellation now too. Those 3's are going to cancel. So we will have 9,800 multiplied by 2. Let's see, the 0 is not contributing. 16 to the 3/2. Denominator is a root. So the square root of 16 is 4. And then 4 cubed is 64.
Why isn't it 1/16?
Why is it 1/16? Is that what you said?
Why isn't it 1/16?
Oh, it is. Thank you. Yeah, that's a 16th. This should be a 16th. That should match. Thank you. Thank you. So square root of 1/16 is 1/4. And then 1/4 cubed is 1/64. Does that look better? Yeah, that looks better. 4 times 4 is 16. Multiplied by 4 is 64. Yeah, there we go. Much better. So then 9,800 divided by 32, whatever that is. Joules. Somebody.
I got 306.25.
306.25, and if we left it as a fraction, sounds like 4 is the fraction, so 1,225? That look right? Let me double check that fraction, but I think that's what you just said with the 0.25. All right, so there are the joules. Any step there you want clarification on? Trough is the hardest one. Notice there's no pi in it, right? Because our cross sections are not circles. Our cross section was a rectangle. Even though the front of the trough is a circle, just because the front of the trough is a circle doesn't mean the cross sections have a circular piece to it, right? The cross section is a rectangle. Rectangle is, length times width, so there is no pi that's going to show up with this particular shape. Let's try the cone. So there's the cone. Let's take a look at a cross section. Cross section right there at a random y. What is the, if we're going to pump right out the top, what is this distance right there?
6
minus
6 minus y, exactly. So this distance down here is y, right? That's what y is representing. Y is representing the height above that, the xy plane or the vertex, however you want to think of it. All right, so then our acronym work is going to be ADD volumes integral. And once again, 9.8 times 1,000. So there's the AD. And then the second D, the distance that our cross-section travels if we're pumping right out the top.
6 minus y.
So 6 minus y, exactly. So there's the ADD part. Pretty darn fast to get all the way to there. Now here's the part that's the more subtle part. We are finding the volume, not the volume of the whole cone, the volume of a slice. So that volume of a slice, we're in here and we're thinking, okay, there's our slice. The thickness of the slice is dy. So we need the area of our cross section, area of cross section multiplied by dy. Okay? Well, to get the area of our cross section, we need to know that radius, which means we need to have a function that's measuring sideways here. We need a function that's going to measure how far away we are from our axis, from the y-axis. So we need to find the equation of that line and isolate x. Okay, well, that's a line through the origin. That's not too bad. Right? We're imagining our coordinate system right there. So the line will have this form, mx. The y-intercept is 0, so it's just going to be mx. The slope, we're going up 6 and over 1.5, so what's the slope? Slope will be
4.
4. We're going up 6 and over 1.5 times x. So we are going to have an equation of y equals 4x is that right edge of the cone. If we isolate x, x will be 1/4 times y. That is the radius. This is the radius of the cross section at a height of y. If you're at a height of 0, the radius is 0. If you're at a height of 6, if you plug in a 6 right there, you get 1.5. So that's measuring the radius at a height of y. That's what goes in right here. So pi times the radius squared. Pi times the radius squared. So that is the area of the cross section at y. So that's a cross section. That's 2 dimensions. To inflate it into a slice, we multiply by dy. Now we have the volume of a slice. So that is volume of slice. Limits of integration? 0 to 6. So we have a bunch of constants in here that all jump to the front like normal. So the 9800. And then it looks like we're going to have a pi out in front. And it looks like we're going to have a 16 in the denominator. So the only stuff not coming to the front will be the 6 minus y multiplied by y squared. So 6 minus y multiplied by y squared. So y squared times 6. Y squared times minus y. So we have that. We have a little simplification out. Let's just wait though. Sometimes other constants come out. We could certainly divide each of these by 4. Let's wait though and just see if there's anything else that happens. Add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent. Oh, we've got that. 0, nothing. 9800 pi divided by 16. Plugging in a 6 cubed,
260.
216. And I'm not going to multiply it by the 2 just yet. So when the 6 goes in here, that's 6 to the 4th. I'm going to make it a 6 to the 3 and a 6. So a 6 to the 3 is 216. And then we have a 6, one more 6, and we've got that 4 in the denominator. So we're dealing with this scenario right now. Nice. And then the 216 can come to the front. Just might make our math a little easier if we do that factoring. All that's divided by 16. So this, when we factor out that 216, we're left with 2 minus 3/2. 2 minus 1.5 is 1/2. We have that. Then we just have to figure out what goes in where here. So the 2, let's divide that into the 216, so that's going to give us 108. 16 here, if we divide out a 4 first, because that's the easiest thing I can see. 4 out of there. If we divide this top piece by 4, we're going to get 2, and then 4, and then 50, I think. That would be 48, that would be 4,900. So that looks right. And then divide out a 2 and a 2, so 54 and 1225. And then that, somebody has to tell me, what's 54 times 1225? So whatever that multiplies to,
66,150.
66,150?
Yes.
Thank you. Multiplied by pi times joules. So that'll be work done. All right, so all that stuff there is just the evaluation. Any question on the setup? Any piece of that setup? All right, I think we're ready to deal with the chain. So let's go back to the chain, or the rope. 60-meter rope, 9.4 millimeters of diameter, rope's hanging freely. The density of the rope, 55 grams per meter. That density is a one-dimensional density that's given to us. So we're dealing with 1D density, not 3D density. So if we're dealing with one-dimensional density, does the diameter of the rope matter? No. That is extraneous. We do not need this because we're imagining the rope as a wire or a thread, right? Because we're being given the density in 1. We're not being given 55 grams per cubic meter. If we were imagining the diameter of the rope mattering, our density would be a 3D density. We'd have a denominator of meters cubed. So that is extraneous. So when we go from 3 dimensions to 1 dimension, we're getting rid of 2 dimensions of length. Our normal ADD volume, if we're going to get rid of 2 dimensions of length, we're peeling off 2 meters, like a meter and a meter. So volume becomes just length. Right? If you have volume, you have meters times meters times meters, and you take away 2 of the meters, you're left with just meters. So that volume, if we go from 3 dimensions to 1 dimension, is just length now. All right. The thing in parentheses is always our representative cross-section multiplied by thickness to give us a volume. But now our cross-section is just a tiny length of rope. It's an element of rope. Right? Everything in here has gone, this has gone from this volume of a slice down to that's just dy. That length is just dy. It's an elemental length of rope. So that's the part, the integral is going to look way simpler, but it's the concept of going from volume to length. We still have acceleration, we still have density, we still have distance traveled, but we've taken away 2 dimensions here and reduced it from volume to length. But that's where the differential shows up, right? The differential is always in that parenthetical quantity. So that length is our differential. So our work is going to be the density. Now we're giving grams here per meter. How do we convert that to kilograms?
Divided by 1,000.
So we're going to divide by 1,000. So, why? So we're going to divide by 1,000 to make that kilograms. So that's AD. So we have AD. And how about the distance traveled? So we've got this 60-meter climbing rope, probably. Because the author of our book is named Bill Briggs, who's one of the most famous Colorado climbers. So you know he's talking about a climbing rope, 60 meters. So 60-meter rope is hanging off right there. If we take our representative cross section is just a little tiny element of rope. So dy. So this is at a height of y. You need to write a y. So there's a height of y. The thickness of this cross section is the dy. Right. So we've got the height above the ground right there. What is the distance that cross section of rope has to travel? 60 minus y. That's how far it's going to travel. So that's what goes right here. So there's the ADD, but there's no more volume. All we have is length, and that's what the dy is. So the dy is that length component, and we're gonna bring up. So we're pulling up the entire rope to the ledge. Now, if this rope was just touching the ground exactly, the work in dropping the rope would be the same as the work done in pulling up the rope. So if that rope is stretched out and just barely touching the ground, you drop it, gravity would do the work in bringing the rope to the ground. If we pull the rope up to the top, the person that's pulling it up is going to do the work. So this will be 9.8 multiplied by 55. Oh, I guess we can simplify that a little bit. 5 goes into there 11 times. 5 goes into there 200 times. Integrating this is going to give 60y minus 1/2 y squared from 0 to 60. 0 will contribute no work. So we are going to end up with 9.8 multiplied by 11 over 200 multiplied by, so that's going to be 3,600 minus half of 3,600. 1,800. It will be half of 3,600 as the result. We can chop off these 2 zeros. We can make that 2 be a 1 and that 18 be a 9. So somebody multiply 99 times 9.8. 970.2 joules. If we wanted to turn to a fraction, we could. But that's still exact. So with the 2 dimensions missing, the integrand actually becomes easier, but it's there's a little bit more subtlety in understanding each of the pieces of our acronym. Let's try another rope one. So how much work is required to wind the entire chain onto the cylinder using a winch? So here we have a 30-meter long chain that's hanging from a cylinder attached to a winch. So let's just imagine our 30-meter long chain right there. Of course, there's no friction. So here we're gonna wind the chain entirely up. So imagine taking a cross section of chain. That cross section of chain we're gonna say is at a height of y. So the distance that that cross section travels will be 30 minus y. And the work done will be the integral of ADD, but instead of volume, we do ADD length because we're in a one-dimensional density case. We know we're in one-dimensional density because it says right there, kilogram per meter, not meter cubed. So we can fill in our blanks. 9.8, acceleration due to gravity, multiplied by the density, which is given to be 5, multiplied by the distance traveled by our cross-section. So there's our ADD. ADD. And then length. Just the dy. We integrate from 0 to 30. How's that look? Makes sense? Okay, so we can pull this, let's see, what's that going to be? Is that going to be 49 out in front? 49, and then when we integrate, we'll get 30y minus y squared over 2, 0 to 30. Plugging in the 30 is going to give us 30 times 30, which is 900. 900 minus half of 900 is half of 900. Half of 900 is 450. So then we multiply 49 times that. And
22,050.
say that once again.
22,050.
22,050, thank you. So there's our work done. Now they ask a follow-up question and they say, all right, now let's attach a block to the end of this. And this block is going to weigh 50 kilograms. So the way we think of this is that we are winding up the chain. And there's going to be work in winding up the chain. Then there's also going to be work in lifting the block. And we can separate the two. We already found the work that it would take to wind up the chain. The work to lift the block 30 meters is mgh. So the work just for the block to be lifted 30 will be its mass times gravity times the distance traveled. And mgh is usually what a lot of books will put it as. So 50 kilograms times gravity multiplied by the distance traveled. So somebody multiply that together.
14,700.
14,700, thank you, joules. So then the total work to wind up that whole system, we're just going to add these two together. And that'll be our total work. So it looks like about 36,750. So that would be part B. Again, no pi in this one. Our cross section doesn't have a circle in it, so there's no pi. Let's So I created this slide. This is interesting to me because I'm not a physics person. And there's two ways to think about the following. If we have our chain hanging, let's suppose we only want to wind it up halfway. Okay, so we've got the chain dangling. We're going to wind it up just halfway. There are two ways that you can think of this. My way was to do it this reality way because I'm a math guy, and I'm like, oh, okay, well, if we're only going to wind up the chain halfway, I've colored the top half of the chain orange, the bottom half black. This is what it looks like once it's wound up, right? The top links are the ones that go to the top. Well, you could then just think of the bottom chunk of links as a block. And you could do, okay, ADD length integral, and we are integrating from 20 to 40, right? Because these are the links that are moving. And then we just add the MGH for the block. That's the way I did it. And then I looked it up, and the way the answer key had it was this way. They just had a single integral, and they had the limits going from 0 to 20. And physics people that I know would say, oh yeah, this is how you would do it, just integrate from 0 to 20. I'm like, but wait, the links from 0 to 20, if you imagine it as a block, those aren't moving, right? They're moving as one unit if you think of it as the block. And so in this case, the reality method is the way it is. This way is sort of in looking at the initial state versus the terminal state. There's still half the chain hanging, and there's no reason you can't imagine that the black links are the ones that jumped up to the top and that the top half is stationary. Obviously, that doesn't match reality, but it works mathematically. So if we do that and we think, oh, well, let's just move these links of the bottom half to the top and let's let the top hang, then it's these links that are moving, so our integral is 0 to 20, and there's no block. This part is not moving, so there's no block that you have to imagine attaching. So you can integrate 0 to 20, and it works just fine, which
Both achieve the same answer.
same answer. So here's it worked out. You can look at them, and you end up with 5880 joules in both cases. But I thought that was kind of interesting. So that's, I think, more how a physics person would look at it. And imagine the final state of the chain instead of actually going through the kind of the physical, actual reality that's happening when you're winding it. So look at that. Take a look at both those solutions. Okay. So our last thing in this section is dealing with force and pressure. I want to remind you again, so our worksheet is due this Thursday night at midnight. So in OneNote, I'm not going to be grading after midnight on Thursday night. So in practice, I won't. When I wake up on Friday morning, that's when I'm going to lock the worksheet. So if you want to work past midnight, and I won't lock it before 8 a.m. on Friday morning. So keep that in mind.
Is that like the first official homework assignment due? And then we have the stuff due on the 12th, right?
Yeah, and then so all my math lab stuff is due on the same day. It's due the day before the exam. It's set to be due on that. The schedule says Tuesday night, but I actually set it for Wednesday night. So it's due the night before the exam, all the homework and the quizzes, so that I don't have to deal with changing due dates because somebody's whatever happened to whenever to whoever. So it's all going to be due at once, which means you've got to stay pretty proactive on keeping up with it. So the worksheet is just chapter 6. It's not going to be the chapter 7 stuff that we're going to do on Thursday. So it's just chapter 6. Thursday night at midnight, really the next morning by 8 a.m. And then I'll grade it really quickly. I'll grade it on Friday, get it back to you, so that then on test day you can do the corrections to get full credit on it. That makes sense? And again, our test is a week from this Thursday, so our review session is next Tuesday. I don't have a sub yet for next Tuesday, but our review day, normally what I do during the review day is go through as many of these review questions as possible. So they're all labeled, they're all stuff that we've done, all stuff that will be relevant to the test. And so I created a video solution to every single one of them so that you can go through each of those, and I walk you through from start to finish each of those review questions. Normally on the review day, we really only cover about 60 or 70% of those. In practice, there's no way for me to do them all in a review class. So at least now you have a solution to every single one of them, so that you can do that. So if you guys want to get together, come in here and turn on the computer and do them together, or just watch them separately, whatever you want to do is totally fine.
When will we know if you have a summer off?
Thursday.
Okay.
I'll know by Thursday. Yeah, I'll know by Thursday. The only potential is Steve Yamakowski, so I'm seeing if I can get him to come and work at least half the problems live. I'll find out on Thursday, though, and I'll let you know. And then on test day, the one thing that tends to cause some rub is you can't use a calculator with an integral symbol. So you can use any scientific calculator, but there is one of those TI calculators, I'm forgetting what the number is off the top of my head, that does have an integral button. So you can't use an integral button. We have calculators back there that you can use that are okay. A lot of the Casios actually have an integral button. So you can't have a calculator with an integral button.
Definite or indefinite or all integral?
Any, yeah. The more fancy ones you can actually do, symbolic integration. The less fancy ones like that, the Casios, they do numerical integration. Yeah, so no integral buttons, because it's not fair if someone is able to check their integrals and someone else isn't. So no calculator with an integral button. All right, so let me just say one thing about our next section. We won't be able to do a problem, but I want to ask you a very important question, and it's I think super interesting. So what our context is going to be that we want to find the force on a wall. This is just an introductory slide. We'll talk about it more on Thursday. So here's my question. So we imagine this as a dam, and water is pressing against the dam. We need to build the dam so that that water exerting the force on the dam isn't going to collapse the dam. All right? So my first question is, let's suppose we have this dam, and we've got water behind it. So we've got this water behind it. Let's suppose the length of this water, the distance from the back edge to the front, let's just suppose it's 10, whatever, meters, feet, whatever, it doesn't matter. So that's exerting a certain force on the wall, on that dam wall. Okay. What if we extend this water further back? Let's suppose we need to dig more and we extend another 10 back. What does that do to the cumulative force on that wall, on the dam?
Increases it.
By what factor?
2. 10.
So increase by a factor of 10, or possibly double. Any other ideas? The reality is that it doesn't matter. There is no increase. If you have 5 feet of water pressing on the dam, or 5,000 feet pressing on the dam, same force. That's what's so interesting about that hydrostatic pressure. Water is pushing in all ways simultaneously, so you can imagine 2 sort of molecules of water. One's pushing the next one away from the dam, right? They're pushing in all directions. So it all cancels out. If you have 1 inch of water, same force as if you had 50 miles of water. Okay, so that's the concept that I want you to be thinking about before we start doing these problems on Thursday. is that it doesn't matter. That's why you dig as far back as you possibly can, because it doesn't matter. The force will be the same regardless of whether it's an inch or a mile, which is kind of shocking. So watch those hydrostatic 2 videos I put up there, because they're super interesting. Super interesting. And I will see you all on Thursday. And I will be here. I'll stay. If anyone has questions, stay. We can do some math.
This is a by calculator, right? I didn't use one.
Yeah, let's see. This is the simplified Casio. Yeah, the integral button is, yeah, you don't have the integration in here. It's usually right in there. So that one's totally fine.
I don't use that.
Good, you get to use it.
What? Amazon. It's the best calculator for calculus.
Which one is that called?
I've got the Casio on my thing.
That one has the integral button. Yeah, that
That
one.
was like tape over and just like.
Yeah, I mean, and most people don't even ever use it really, but. Yeah.
I use it all the time in college.
Oh, good. Yeah, most people that stumble into calculus don't even know how to use it.
It's freshman year of high school.
And it's
Got me
well.
through- Got me through the SATs and
Sure, yeah. Yeah, let's take a look at it. Let me turn off the recorder.